Hey all, my name is Geordie Rose, and I am starting a new podcast series, which is going to be me talking about basically anything that I am interested in at the time. It's going to be very eclectic, I'm sure. Lots of different cool things to think about and discuss. Um, this first one is about a topic that I've been thinking about a lot recently. It actually started from an old idea that I've been thinking about for a long time about a way to potentially use quantum computers to do something useful adjacent um, in the early stages of their development. And the that subject itself is interesting, I suppose. But the thing that I've become more into recently is the topic of agency. So you might probably have heard about agents, and uh, an agent in the reinforcement learning context is an entity, and what that actually means is actually pretty interesting. That takes actions. So it's defined by the fact that it takes actions. It's all it does. All it does. It's kind of all there is, but it's an abstraction that allows you to examine the mechanisms of action taking. So why does an agent do something is a very old question in the study of ourselves, and is at the root of most of the big problems in philosophy. Things like free will, do we have the choice to take the actions we do? Um, what does it mean to be conscious of your actions versus not? Uh, what does it mean to be a good person and to have a life well lived? Which is a way to think about valuing different actions over others. So all these questions are very old. They're very important. I think they're interesting to pretty much everybody. And up until recently, they've been kind of the province of sort of vague, wordy, stuff that you typically find in philosophical discourse. Which, I mean, there's a place for it because it's kind of like opens the door a crack. But I mean, at least for me personally, I'm much more interested in things that you can actually build, where whether or not your ideas are correct can be tested in a way that is somewhat aside from my desire for them to be true. So I think one of the reasons why AI and machine learning more generally has taken off is that it's a testable science. You either detect the cat or you didn't. um, and in questions like these, where you're talking about very deep things, where people have very deep-seated prejudices and biases, it's impossible to make real progress unless you ground what you do in actual real things. So, um, where I started with this was this business about trying to figure out a use for quantum computers, but along the way, part of the machinery that I needed to build was a system for making decisions, which you can think of, at least on its surface level, as an AI, so an artificial intelligence, an agent that makes decisions about how to play a game. So the games that are of the sort that I'm looking at now have some peculiar features that intersect with quantum computing. But none of that is relevant to what I'm going to show you today. This is about trying to explain a part of a modern game playing agent, which is called AlphaZero, which was introduced by DeepMind folks around 2016, 2017. And it's fascinating, kind of captivated my interest, and has been the thing that I've been kind of digging into over the last couple of weeks. And in digging into it, what I do when I do that is I kind of like go through every single line of code and I try to figure out exactly what's going, and then I try to explain it. So this is about explaining an important part of the AlphaZero process, which is how does the agent actually make a decision to make a move. So if I'm staring at a chessboard or a Go board, or I have to make a decision in life, like I'm going to do this or that, what is it actually doing when it makes that decision? So we can't introspect our own decision-making processes very well. We can a posteriori make up excuses for why we did the things we did. But those aren't actually why we made the decision. What I'm very interested in is the technical guts of how can decisions be made and how can you learn from your decisions, because they have impacts in the real world. And you can measure those often. And you can provide feedback to the agent, which can then learn to be better. So AlphaZero is a fascinating and brilliant way to imbue an agent with the ability to make decisions about what actions to take, in a way that it can get better over time. So it gets better. And in many games, there's demonstrated superhuman performance, like in chess and Go and a few others. So with that as a kind of ground, I won't usually go on this much when I'm introducing these podcast things, but because this is the first one, I felt like I could ramble a bit and introduce it. So this is a visualization of the Monte Carlo tree search process within the AlphaZero context, and I'm going to show you how it works. I hope you enjoy it. Hey folks, I'm going to show you how the Monte Carlo tree search algorithm works. The example that I'm using is for this game called Tangled, which I won't go over because I've written a lot about it already. But just like all games of this type, there's two players. We'll call them red and blue, and they alternate taking actions. And at the end of the game, there's a winner or a draw. So either red wins, blue wins, or there's a draw. And in this particular case, the game is being played on such a tiny graph, this thing I call the ridiculously small graph, which is just 3 vertices connected by 2 edges. The edges connect the middle and the left vertex and the middle and the right vertex. And so these the total game tree is relatively small, so we can actually see it on a screen. So it's got here what I'm showing here. Okay, so let me just dive into it, and I'll explain some of the things that I'm looking at here. So the first thing that I want to show over here on the left is that the initial state, that's this thing over here, which when you start this algorithm, you're in the current state of the world. So imagine we're just starting a game. It's a fresh board. Nobody's played yet. And in Tangled, the fresh board means that none of the vertices or edges have been selected. There's just nothing happening yet. And that in this Monte Carlo tree search world is called the root state. So the root state is the one that's the current actual state of the world. So imagine we're starting to play the game and there's just an empty board. Think of it as chess or whatever. This is just nothing has happened yet. It's just the initial state of the game. But it's red's turn. So these arrows here at the top are whose turn it is. So red will go first, then blue, then red, then blue. One of the features of Tangled is that there's a fixed number of moves in a game that depends on the size of the board. And in this case, the board is so small that there's only 4 moves, 2 for each player. This thing up here will become more clear shortly why I've put this up here. But these are, I'll just tell you what these mean first, and then I'll show you how they're used. So this N, S, so all these things are functions of S and A. So S is the state that you're in, and A is the action you take from that state. We haven't taken any actions yet, so none of these matter yet, but the state that we're in initially will be this guy, and then we're going to take actions from that state. So what this means is the N is the number of times action A is being taken from state S. P is what's called a prior probabilities in this context, which is the belief that the system has about the goodness of taking action A from state S. and this P is going to be the output of a neural net. So in Monte Carlo, in AlphaZero's version of Monte Carlo tree search, there's a term which comes out of the neural net, and I'm going to show you in more detail how that works. But this is the prior probabilities. Q is the system's belief, or the agent's belief, about the quality of taking action A from state S. So this is a kind of a numerical view that the agent has about how good action A is to take from state S. U is an exploration term. And again, I wrote about this in the blog, so if you want to look at it more carefully, U is the exploration term. So it's the term that forces the system out of just always picking the best possible belief of its quality and to explore other possibilities. And this PUCT thing is just Q plus U. So this last term is just the sum of these two. And this last term is going to be the most important of them of all, at least while we're running through the algorithm, because it's the way that the system picks what action to take from state S as it's going through its tree. Okay. All right. So when the algorithm starts, it adds the initial state, which is like the current state of the world, to the search tree. And whenever that happens, that thing becomes what's called a leaf. So a leaf is the latest state to be added to the tree. So when you're at the beginning, there's just nothing. So when you first start the algorithm, the first leaf state that's added is also the root state. So this is a case where the root is the leaf. It's the first thing that's added. And in the AlphaZero way of running through this Monte Carlo tree search, every time a leaf state is added, you put the state into your neural net, which is the thing that you've concocted to help the Monte Carlo tree search along, and kind of the point of the AlphaZero process. And this neural net outputs two things. So one is this vector of numbers, which are probabilities of taking the different allowed actions. So in this particular game, there are 9 allowed actions. And so each of these represents one of the possible actions that could be taken from 0, 1, 2, 3, and so on. And initially, the neural net is basically random values. So it's just junk at the beginning. You're just going to get some junky thing. And you can see here in this case, they're actually all more or less the same. So the neural net has just outputted some random noise for that. And by the way, this stuff that comes out here are these P's, except when the root is the state is the root. So in this case, it's when we actually look at these, they're not going to be exactly this, because there's going to be another term added, which is called Dirichlet noise. So we'll see that come out shortly. And this other thing here is called the value. So the value is a guess at the quality of the state. The only way to know for sure whether the value is the ground truth for value is the terminal state, so the game is actually ended. We don't know that initially. So this is the neural net's guess at the value of the state, and so it's basically like trying to see guess how good the state is. Okay, so we started by adding the root state to the tree, so it becomes a leaf. We send the leaf into the neural net. We get these guesses, and then the system advances a little bit. So I'll just advance this video. And the next thing you see here is a bunch of numbers, and you can see the first row here are all zeros, and that's because we haven't yet added this action yet to the number of times it's been added. So if we just bump it forward a little bit, you can see that one becomes 1. So if I get it just right, there we go. So when the first one is added, this is going to bump to 1. These numbers here, this list, are the probabilities that we saw before, which remember they were all equal, added with some noise. So if I add some noise to this, what I got in this case are are these numbers. So this here is just that initial neural net plus some noise. And the reason why the noise is added is it enforces, as the algorithm churns, the trying to choose all of the possible initial states. So all of the things that you could do from the root, the system wants to try all of them to encourage exploration from the root state, so it doesn't get locked into some particular choice and miss something that's good. Okay, so the next thing that happens, so this little thing here is supposed to be the root, so it's the root. So the next thing that happens is it randomly chooses one of these with these probabilities. So you can see these probabilities, the highest one is 0.23. So it chose the highest probability one. It didn't have to, but it happened to in this case. And so it takes action 0. That's the top action, say 0, 1, 2, 3, and so on. It takes action 0, and that leads you to this state. So action 0 was coloring this edge black. So that now becomes the leaf. And the process is, once the leaf is determined, the leaf gets fed into the neural net, and another vector is formed here, which is the prior probabilities from this state of taking all of these different actions. And this is a guess at the value of the state. You can see the value of the state here. So as we crank forward, you can see that here that value in the top line is actually minus this. And the reason for that is that this is a zero-sum game where players take turns. And so the way to track value is that the value from one turn to the another is the negative of it, because we're looking at it from a different perspective. So when you're from the perspective of red, say here, well, this value here was positive. So that's from the perspective of blue. But red has the exact opposite view of the world. So if something is good for blue, it's bad for red, and vice versa. So the value of this goes back here, and this Q is going to be the average of the values of all of the states that were seen by taking this action. So if we follow this action path, the average of all of the values is going to be what this is. And so right now it's minus this, and the minus sign is because it came from a blue perspective. So the next thing the algorithm does is it goes again and it finds another leaf state. Now, why did it pick this one? It's because these numbers here, this last column, this PUCT thing, which is the sum of columns, the middle column and the one right next to it, the algorithm always picks the biggest number here to add to the tree. So this one you can see is 0.28, which is the biggest of all of these numbers. And it's that way because this U term just happened to be the biggest here. And so that it adds this state to the tree. That becomes the leaf. And again, the leaf is now fed into the neural net, and a bunch of numbers are generated, and a value is generated. And now this value is negative. Remember, this is just noise because the neural net doesn't know what it's doing yet. And so that is going to be pushed back here at the next step. And you can see now it's plus. And so now the system is looking at the current state where it's going to ask, well, what am I going to do here? So the biggest number, it turns out, is still the top one. So what it's going to do is it's going to take the same action, the top one, and then it's going to go down one more branch in the tree. So you can see it went from here to here, then to here. The reason it didn't stop here is already in the tree, so it's not a leaf, so it went one more down, and now this is a leaf. It wasn't in the search tree before, and now it is. By the way, you can see these lines that are kind of appearing. So the way that I've done this animation is that the lines get darker the more you take them. So they're kind of like, grooves or something. Okay, so you can see here that now that this is the leaf, we got a positive value from the perspective of red, which becomes a negative value from the perspective of blue, which then goes back and becomes a positive value. You'll see that shortly when it updates for the next one. And remember, this is now going to be the average. So it had a value before, and now it's going to get bigger. So you can see it got bigger there, and that's because it averaged the value here and the one it had before. Got a little bit ahead of myself there, but Now the question is, where is it going to go next? Sorry, I'm a little bit ahead of myself. Right. So if we're in this state here, and you look at see what's the biggest number, it's hard to tell because these are both 0.29, so we don't have enough precision to see, but the system does, so it picks this one. That was the highest one. And this becomes the leaf. It's fed into the neural net. So this whole thing keeps going. And the number of times it keeps going is this parameter big M that I described in the written part of the blog post. So big M is the number of simulations. This is kind of usually what it's called. And so you keep doing this big M times, and the process is always the same. You look at this column, you pick the number that's the biggest, you take that action, and then you repeat it. So I'm not actually showing yet the PUCT numbers for the other states. I will eventually, because I wanted to focus on the action taking process for the root state. So all of these is just thinking about what to do still. But they're there, and it's the exact same thing, is that you're always choosing the PUCT thing. So I'm just going to press play on this video, and what it's going to do is it's going to kind of run through the algorithm. So it's just doing the thing that I said before. Every time there's a leaf state, it sends it into the neural net. It computes the prior probabilities and the values, and it just keeps going. So I set this particular run to use 50 simulations, 50. And by the way, it doesn't actually take this long when we're actually running it for real. I slowed everything down and put a bunch of pauses in so that we could actually kind of like look and see what was going on, just to make sure that everything's working. The reason I started doing this visualization to begin with was just to kind of make sure that the code that I wrote was actually doing what I thought it was doing. And I actually caught a couple things that I was doing that were bugs, so it was quite valuable. I'll pause it once we get to a terminal state, assuming we do in this first run through. There we go. So let me just pause that. And so the terminal states here are the states at the end of the game. So they're the ones that you want to see, like who actually won. And the way that I show this is that the terminal states that are draws, I have this gray blob. If red wins, it's a red blob, and if blue wins, it's a blue blob. So let's see if we can go through to assist a terminal state that was one of the wins, because I want to show you how that works. There's another draw. Hopefully we get one here. I haven't actually watched this video yet, so I don't actually know whether we get to one of the terminal states or not. Oh, I think that was it for the first run through. Let me just double check. Yep. That was. Okay, so in the first 50 simulations, this was the end of the tree. So once you've gone through all of the simulations for the step, so we've done 50 in this case, and we've developed a search tree, which is part of the game tree. It's not the whole thing, but it's some of it. And the system's developed some intuition about maybe what the right things to do are. In this case, it's hard to see how that could be because the neural net's just outputting random shit, and we only actually got 2 states that were giving us ground truth about what the actual values of the states are. But it's got some notion, and the way that it works now to determine what action to take is you look at now at these n numbers, the ones that are on the left. And in Monte Carlo tree search, there's usually a parameter which is called temperature, which tells you what to do with these numbers. So for those of you who are physicists, T equals 0, the 0 temperature answer is you always pick the path that has the largest numbers of actions taken. So the action that you pick, the one that you want to take, is the one that was taken most. So that's T equals 0. T equals 1 in these units is the probabilities are proportional to the number count. So for example, there's 50 total, so these numbers should up to 50. If you set T equals 1, it would be 12 divided by 50 would be your probability of getting this guy. But you could also pick this one down here, which is 3 out of 50. So it's not high, but it's not 0. So usually the way Monte Carlo tree search works is that at the beginning of the game, and this only has 4 moves, so it's hard to it's all kind of end game, whatever. It's just a tiny little example. But usually with games, the way it works is that for a while, so say the beginning and middle of the game, you set t equals 1. And what that means is that the system explores more possibilities. So it doesn't always pick the action that it thinks is the right one to pick. It explores around those. But then at the end game, when you get near the end, you set t equals 0, which means it's always trying the answer that it thinks is best. And you're going to see shortly why that might make sense as I go into the later stages of the algorithm. So all of this was just to pick the first move. So this was Red's spending 50 simulations to try to figure out what to do. And he's gonna probably pick the action 0, the top one, because that one has 12. So it's likely that he's going to pick it. Also, you see the line is darkest, so that's So let's just see what happens. So we're gonna just run this through a little bit, and yes, okay, there it is. So what's happened here is that Red has picked this action, the top one, which has put us in this game state, which now becomes the root. So everything that I started with from the beginning, where the root was the initial game board, we now do the exact same thing, but now the root is the state that we moved to from taking the action, and now we're playing as blue. So we're playing the other side of the game now. It's the same agent, but we're playing blue. And so the question is, what action do I take from this state? Now, in Tangled, there's a rule that if there's only one unclaimed edge and you haven't played your colored token yet, you have to play your colored token. So the reason I mention that is if you see here, there's only 3 actions possible. So there's this one where I put my blue token on the right. There's this one where I put it in the middle, and there's this one where I put it on the left. So blue only has 3 choices, and you can see here that these 3 states have already been visited several times in the previous run through, and we keep those. So there's no reason to throw them out at this point because nothing has changed yet in terms of how good the system would be at predicting what's good, because we haven't done any neural net training or anything. That happens later. So we're just going to keep going. And now we're going to do another 50. So what will happen here is these numbers, these n's won't add up to 50 anymore. They'll be 50 plus the number that have already been tried. So I'll just press go here. So we've already actually done one here, and I'm going to show you this thing because this is a good place to show this. So the move that this guy took, if we can trace it back here, was to move here, and then here, and then here. So that was the descent through the tree, ending at this terminal state, which is a win for Red. So the value of this state for Red is +1, and the value of the state for blue is -1. So the +1 here goes back to -1 for blue, to +1 for Red, to -1 for blue. So when this gets back propagated back here, the value of this guy is going to go to -1. There it is. And so the way to think about this is that blue made a move, and the outcome was that Red won. And so that fact got back propagated back to this state, which means that it's unlikely. So if you look here, the Q number in the middle is big and minus, big and negative. So what that means is that the thing really believes that this is not a good state to take from the perspective of the outcome. It's still got a pretty big exploration number, but this number is fairly large and negative. So the way that impacts the next choice is that the PUCT thing is now going to try this one, because this one is the middle. So it's going to try putting its blue token in the middle to see what happens. So let's just hit play here and see what happens. Okay, so it also ended up in a bad state, which was this red state. And so again, you can see here that the Q got more negative, and this number went down again. So now it's going to try the top one. So you see what's happening here, right? Is that as it tries things, its answers are now being grounded in the ground truth, which is the outcome of the game. And so it's finding out what's happening when it takes these different moves and adjusting its behavior to try to find something that isn't giving it such a bad result. So let's see what happens when it takes the top one. Aha! So there, look, it got a blue. So what that means is that this was good for the original action taker, and that's going to be propagated back to here. So this let's see, how are we gonna +1? So this is -1, +1, -1, +1. Yeah, and so the whole thing continues like this. And if you want to see like what's happening, just focus on the rightmost number, and it will always take the one that's the biggest as a combination of like exploration and exploitation. And if you want to figure out why it's taking this, is because these are preferentially ending up. See, these lines are darkening into the blues. So it's taking this move over and over again because these ones are preferentially ending it in states where this move is a winning move for blue. So it's going to continue to explore again for 50 iterations of the algorithm. And these lines are getting darker and darker because it's just very, very favorable for the system to take those paths. So I think we're actually in the terminal state here. Let me just see if anything is happening here. Okay. Oh yeah, we're still going, still going, still going. I'm just fast forwarding it here so we can get to the point. There. Okay. So at this point, I'll just pause it. At this point, we've done quite a few simulations, and this one is by far the best move for blue to take. So blue's going to take that move, and what that means is it's going to take the action that leads to the state. And when it does, that state becomes the new root. So we've now made two moves in the game. The agent made the move for red. Now it made the move for blue. And now the exact same thing is going to happen again. We're going to do 50 more simulations from that new root state, which is the current state of the world, which is one blue, a black line. And now red has the exact same issue that blue had before, is that red needs to place his token, and because there are only two places that red can place his token, it's going to be either here or here. So there's only two choices now for red, and they've already been explored quite a bit. And you can see that the outcomes so far have not been good, but maybe that will change. Let's just hit play and see what happens here. So let me just draw it forward a bit. There we go. So the red made this move, and now the final move is going to be blue's move. And by the way, the reason why these other ones weren't explored at the previous step is that blue owns the last move. So from the choices that are made here are from the perspective of blue. So if blue can make a move that's going to win, it's always going to make that move regardless, or barring exploration, but it's going to focus on the kinds of moves that make it win. So this is now the root state. It's the same thing. Now there are only three choices. You have to color that other edge. Those are blue's three choices. Blue could make a choice that ended in a draw, a win for red, or a win for blue. So it's going to choose the one where that's the win for blue, which is this bottom one. And you can see this overwhelmingly large number, which is 97, is the number of times that this path has been taken. So it's going to choose this one. And then you're going to have a full game played. So going to see like at the end of the day what happened here. We started from an empty game board. Red made a play after doing 50 look-throughs, then blue, then red, red, then blue, then red, then blue, and we ended up in the final state. And so this path through these root states becomes an actual game that's being played. And later on, I'm going to show you how that's used to train a neural net, because now we actually have some ground truth. We have red made this move, blue made this move, red made this move, blue made this move, and we ended up in a win for blue. So what does that say? Well, the moves that blue made were good ones, and the moves that red played are probably not. So we can use that to retrain the neural net in order to give better, more accurate guesses at the probabilities and the values of the states. Okay, so mostly this was just for my own amusement, this visualization, but I'm going to make another one to try to show you how the neural net training works, because this is what's called self-play. So when you do the AlphaZero algorithm, the first step is to have the system play against itself a lot. And the reason for doing that is to collect the data for training the neural net in the second step. And once you do that, the neural net gets better, and then you can self-play again, and the system gets better and better and better and better at doing the thing. So this is just the visualization of the self-play part of the process. Okay, well, thanks, friends, and look forward to showing you the next thing, which is how the neural net training works, and then I'm going to try to figure out how to show you how the system is getting better over time, and how the predictions of the neural net gets better and better, and eventually converges on almost being ground truth as the system gets really good. Okay, thanks, friends.